You know what it is? You know the number. I got the number. It's like, I think it's something with the 5 in there. I'm pretty sure there's a 5 in there. It's a Fibonacci. 1.61, but it's like, it's a fucking irrational number.
No, I mean like that was necessary.
Right, no, but there's an explicit, that's what I'm saying, like it's like 5, I forgot what it was, I think 5 over 2 or something.
Yeah, 170.
Yeah, it was like 5 over 2. That's crazy, like why that specific number? What about it?
If there was any other number,
I mean, but you can say anything, it's because it's unique.
Trying to get started here. A lot to talk about. I got about another 2 pages of notes more than normal, so I'm just kind of fast because there's a lot to talk about. Remember today's exam 3 review. So something's wrong with the camera, and it doesn't seem to be charging properly. But I also noticed it has. Sometimes it just doesn't tell me what the real charge is. I don't know why. So if you guys, right by there, if it beeps off, you can let me know. And what I'll do is I'll plug it in. I can put it about here. And it's awkward, but it does work because I had it happen to me before. So anyway, only 2 lectures left. So I don't know. How many of you know about lithium-ion batteries? I mean, I've charged and discharged and charged that thing, God, 400 times maybe. That certainly sounds like a lot. So maybe that's what ion. If any of you know this, tell me. Is that what lithium-ion batteries do when they die? They just don't charge up all the way?
Yes.
It sounds right. So anyway, so I think hopefully it's a fix. But we're done with this class anyway. We're essentially done. Today's review anyway. Let's see. Now, as I promised, I will not have any of that symmetry. I mean, I only spoke like 10 minutes on that symmetry stuff. So hopefully Monday and Wednesday we'll do. You know, one thing I don't like is I don't have a lot of time to spend on it, so I can't show you why it's so meaningful. But it is. Maybe I will. I just don't know. It just depends on how fast I go. And I don't want to go too fast at the end. So none of that's on the third test. It may be. I'll have one question on the final on the symmetry stuff we were talking about, and that's very easy. It's totally not mathematical, right? So it's a bit of a break. Okay, this test. This test is going to be a biz knocker. It's easy, but when I was reviewing, when I was writing my notes, I just wrote them today so it'd be all fresh. And as I was writing the test over the weekend and yesterday and whatnot, God, we did a lot of random ass things that none of them were connected. That hurts, right? Because it's just not like, you know, when we were doing thermo for test 1 and 2, it was all the same thing over and over and over again. I think that really helps. It's like you're constantly practicing the stuff you did yesterday, today, and then the same for the next day. And that really helps you get it all down. And that totally did not happen here. So, and there's not much I can do about it. I was actually double checking other departments, other chemistry, you know, PChem 1, and we're covering the same thing, which again, whatever. It's probably better for you. So, anyway, that's just how it is. So, again, I've got a lot to go over. And of course, as you've gotten to know me, you know I'm going to drop several answers during this next hour. I can't help myself. I'm not going to say what unless I do this, which I will. So again, remember, here's a bit of advice, since I know it's on the test. I got like 2 or 3 more questions to write, so I can't tell you everything. But look at the problems 8, 9, and 10, right? Problem sets 8, 9, and 10. Because I was kind of stuck on material, I kind of relied heavily on those, just even to remember what we had done. And I'll be pretty straightforward about what is and isn't on the test. So, anybody have a question here before I get rolling on? I know several of you have emailed me, and I haven't emailed you back. I've just been kind of busy. Oh, don't kill me. I don't have your homeworks. The grader just couldn't do it. So I know that's a real screw over. I'm really sorry about that. You have the answer key up. I do have the lectures up as well. I was a little slow on that. I'll make sure this is up immediately. Her exam, her PhD qualifier, if she fails it, she's kicked out, and it's coming up really, really soon. So I told her I wasn't happy about this, but I have to kind of side on her case this time. There's nothing I can do about it anyway. It's just that, you know, this test isn't going to wipe you out, but hers will. So sorry about that. So I told her, you know, if you TA for me again, don't do this, but then again, she's not going to have another qualifying exam. And if folks don't, you know, I really encourage you, well, I've said many times, to go on to grad school because I'm just surprised how probably there's still several of you in this room who don't know that you're paid to go. You do not pay to get a PhD in chemistry or biology or anything that matter. You only pay for dental, pharmacy, and medical school. And pretty much any other type of graduate school is not only free, they pay you. It depends on how much. Mathematics, they don't pay you very much. Chemists, we get paid pretty high. Bio, grad school, they get generally a little bit more money. That's about $25,000 a year. It's not great, but I mean, it's enough that you can pay your rent, you can go on vacation once a year, and you know, you're paid to take classes. So you get to be a doctor and there's no blood, unless you're the statty type. Or if you work with animals, which some people do. So, anyway, okay, so I got a lot to talk about. I'm running my mouth about nothing. What's not on the test is, I'm not going to write it, you don't write this down, let me write it down. This is not, because it's not on the test. You know, the X, the Y, a constant Z, obviously that's not on the test. That was on first and second test, and it definitely is going to be a big part of the final. Now, all right, let me just erase it, because I don't want you getting confused with that. Where did I start? I started with excess functions. Excess functions. Okay, that's the mixing volume, the change in U of mixing, the change in H of mixing, change in G, which is minus T, change in S. I'm going to write all that down. Now that kind of did overlap the second test, but it was awkward. If you recall, I introduced it, asked a little bit of questions on it on the second test, like one, but then it appeared in the next problem set 8. So I do have that on this test. That's a little funky, but lack of material, in all honesty, I kind of had to. Okay, so don't forget this, delta mix Z. Now, we didn't really do anything with this equation. Yeah, we did. Now, let me remind you. I'm going to stick with two things. And I got the number of moles. And I've got the partial, remember that partial volume, minus the volume of, here, let's do it like this. This is the volume of the actual solution. And this would be, this is kind of funky here, plus this, right, you see what I'm doing? That plus that, this is the vol of, let's say it's A and B. Okay, so again, I've got a liter of water, a liter of ethanol. So this part, when solved, when calculated, this part would be 2 liters. All right, but then I mix them together, and I don't get 2 liters. I actually get a little bit smaller volume, and that's this part. It can be positive and negative, I don't know. So, and again, we didn't really do anything with this. And don't forget what is this, partial volume? That was like for water and water. This is the example I used, water and water. You add a mole of water to water, it increases by 18 mils by definition, and as where we define the milliliter. And if I added water to ethanol in excess ethanol like a pool, which would be awesome, I'd actually only add 14 milliliters. So that's this guy here. Right, so now, remember, we never really did anything with this. What we did do, and I do have a question on the exam right now, and I'm a little neutral on keeping it, but sometimes you don't have to say lack of material. We did do this thing. And you had to do this on problem set 8, so just review that. Remember, these are, what I do kind of like about these is that it forces you, it's not necessarily easy to remember some formula and just use it. You kind of have to just kind of mentally walk your way through it with units guiding you, and I kind of like that. So I'm kind of leaning towards keeping that one. And so what you often did was, if I was clever, I gave you a total volume by, say, density. So you decided you had, I don't know, 100 mils, and then therefore you had 90 grams of a material. That was your decision. And then maybe you got the grams of A. Again, I'm always just going to do AB. And you divide by the grams per mole. And maybe I should put that label because it looks like these are the same thing. They're not the same thing. I divide by the molecular mass, right? And then somehow I gave you BA, the partial volume, and that would be mils per mole. So then I gave you B, and I gave you as grams per mole. So don't forget that's what that is. Don't let your notes confuse you. Partial volume, which had to be given to you, total volume. So again, just to get the problem set A, I showed you all the ways I could do this. I could have given you, again, density. So you said 100 mils here. Then you would have some percentage of 100 divided by the molecular mass, and 1 minus that percentage divided by the molecular mass. There's just lots of clever ways. Often, these are done not in mils per mole, but mils per gram. I showed you both. Again, just, now you see why I focus on units so much. Don't even try to remember how to do this. Just familiarize yourself and then make the units work. So it's a giveaway question. I don't want to do too many giveaways, but you know, I want you to have a couple. And that way, you know, you have a decent score. Okay, now, remember that in ideal, so then we got the ideal solutions, and this is also on the test in some ways, and we said that A and B, I'm always going to stick with just A and B. A and B have very similar interactions, or not similar, the same interactions in terms of like how the dipole moments and all that jazz, you know, how they bump into each other. And that means when you mix, there's no change in either's chemical potential, so the total is 0. And then we decided independently, there was 2 criteria, that they were roughly the same volume. I'll use liters just to give it a unit, it doesn't matter. So they had the same volume, molecular volumes, took up the same molecular space. So there was no, so this, this was 0. This guy right here, this is why we never really used it, by the way, for anything in particular. And therefore, I don't quite remember, this is on the test, but how I express it, I had to, and I don't quite remember. Just writing it yesterday. So delta mix H is delta mix Q, sorry, I need to remember that, plus P, delta mix B, and that ends up being 0, of course, we'll give a unit. There you go. 0, B delta B, because we're not going to change pressure. Constant pressure world, right? Remember that we were, for the most part, we're working at SDP for this whole third part, and delta G is what matters, so let me do delta G. So it turns out that delta G was going to be minus P delta S, because I've already said delta H is 0. Right, minus P delta S. Delta H we decided was 0 for an ideal solution. Remember, I'm only doing ideal solutions right now. And the way we did that was kind of funky. I'm going to do that so you remember what delta mix S is. Again, I've got 1 or 2 more questions to write, and maybe I'll put this on there. I haven't decided yet. Okay, so then entropy is extensive, so of course I know that I better see mass, moles or mass. So again, I'm going to have A and B. I don't remember. Actually, I even forgot this one. So a lot of parentheses. I had the volume of A, and it's being divided into some total volume. So remember, I'm using a gas-like equation, essentially, to describe a solution. Minus B, R, Ln, BD over the total, double parenthesis. And remember that this actually, I have it on the cheat sheet, maybe a little late to the cheat sheet because I still got to write 1 or 2 more questions. This ends up being nRT, chi A, Ln chi A, plus chi B, Ln chi B. So n times the mole fraction gives me that, and the justification for this was that since it actually does come down, this isn't on the test, but it does come down to the fact that since volume of A is equal to the volume of B in terms of like its molecular volume, that then this has to be mole fraction. And that is very vigorously true. It's childishly true. Okay, so that's where I get this. Remember, it's an ideal equation. And so when we have non-idealities, we can do a couple of things. We can, the first thing we did was use Henry's law. And basically, we started measuring the vapor pressures over the solution, measured the vapor pressure of A, vapor pressure of B, calculating chemical potential, which is just this divided by the number of moles. And that was one solution. It was practical for solutes and not solvents. Remember, this is ideal, so it follows Reynolds law. Remember all that jazz? So this is a Reynolds law result, good for solvents, bad for solutes. At low dilution, you use Henry's law, which basically is the redefinition of these guys in terms of mole fraction times Henry's law constant, which is just like a redefinition of partial pressure. I hope you remember that, because I'm just kind of rambling at this point. And I hated that, because I find that just, oh, this equation didn't work, so I'm just going to insert something there to make it work, and then the devil is in the activity. Activities are just when this just doesn't work at all, and I put a number there and there, a unitless number, that just makes it work. And that's literally how it works. All right, then we had some justification for activity, which was that this was not zero. And we had that phenomenological equation that actually was on the last test. But then we were able to, then I can understand activity. I understand that it has a logical source, and but it still sucks. So anyway, all right, so I hope you remember all this. And okay, Henry's law, the one thing that Henry's law is useful for, calculating the amount of gas in a liquid, which was kind of, wasn't important then, is important now. I gave the Brooklyn Bridge example. And that's when, okay, remember that Henry's law gives solute A a new partial pressure to multiply by mole fraction, which ends up going in this guy's place. And so that was given the letter K, and it had the form of X kilopascals. Okay, so insert a number there. There were very large numbers times the kilograms of your solvent, and let's just make it easy. Just make it water. Right. So if I use this, I will of course use water because that's the only one that's relevant, and then divide by the moles of the gas, whatever gas is present. And right now, I'm not using this on the test, so obviously I can see how to use it. I would take, obviously, something was bottled, including your blood is bottled at a certain pressure. The bottle contains a certain weight of water, and then whatever gas this is will tell you how many moles of gas come out. So I can already tell I take basically atmospheric pressure, however many kilograms of water, I divide by Henry's law constant, and the units give me number of moles of gas. Right now, not on the test, that's very important, right? But this is, I'm probably going to go with one of these, I can't jump anymore, one of these partial volumes, or if I just feel like doing something different, I would go with this one, but I wouldn't do both because they're very trivial. And of course, we talk about, I'm actually going to wait till the very end to talk about colligative properties because they're on, the colligative properties made it to the test, but not just those stupid equations because I hate those. Okay, so there was all this jazz, and then I did all this because it's related to everyone's most hated subject. Here's the hard question on the test. Equilibrium delta G's. So, equilibrium delta G's, that's the monster in the room, right? So, right now, the test, so I can't really do much of a derivation. There really wasn't, what derivations did we even do? Hardly any. Basically, I just kind of borrowed that. And so there's not much in the way to do with a derivation in this entire test. So right now, I'm leaning towards having a derivation section, but having that one there in its place. So it's not really a derivation. But obviously, this was the hardest part. And that, I believe, was problem set, that was actually on problem set 8 as well. So remember that delta reaction G was the same as that in the table in the back of the book. I know I go on, and that little symbol means that's the Hess's law calculation, and these were all per mole, because we did this in the form of chemical potential. And then you have to take the entropy of mixing, which is this guy here, and let me do, well, now I have to give you an example. What are we going to do? 2A goes to B. I've already done this one. Let's do that example. And I also am going to keep these gas phase. Because if these are something reacting in solution, I really can't use partial pressures. I have to use activities, and then I have to just give you the number, and that's just stupid. So I don't like that. So, okay, in the case of a gas phase reaction, I can calculate this correctly. I mean, this is really, really accurate, very close to the truth. I know that I have the partial pressure of B over its pure partial pressure, which just means that it gets a little star. And then I'm done. A is disappearing. Its stoichiometric coefficient is -2. So this guy's going to be squared and it's going to get flipped. Make sure you can set these up. If you can set it up, I'm going to give a lot of partial credit. All right, even if you get stuck further. Okay, and now again, I don't, this sets up the reaction, but I don't really care that much. I'm going to set that, this is a gas phase reaction, I'm going to put it in a balloon, I'm going to start with 2 moles of A, and all I care about is how much B I get. I mean, why am I doing this if I don't want products? It's ridiculous. So what's good is this becomes 0, and so, sorry, I should do it this way, don't worry about it. But at equilibrium, you know that the reaction is minus delta reaction G, which I'll give you, by the way, per mole, because it's really a chemical potential. And this guy is actually also K by Fenwick's law. And now I do have this on the test. Now, the hard part, mole fractions, right? What is the actual mole fraction? How much products do I actually get? It's actually on the test. So don't be too scared. Trust me, I'm going to give you a big hint. But let's work through this example. This example is surprisingly a little difficult. Okay, so remember, I'm going to start with A and B. Remember the little table. And I think I can provide a little table for you to begin with. Let's start with 2n and 0. Okay, then I'm going to lose some. So if alpha, remember, so we're trying to calculate alpha. Alpha 0, nothing reacted, so I still have 2n of A. Alpha is 1, the full reaction, I have no A left, and I would have n alpha of B. So that's the start, that's the finish. And therefore the total, because I have to get the mole fractions, 2n minus 2n alpha plus n alpha is 2n minus n alpha. Yeah, at any given moment, let's make sure if nothing is reacted, I have 2n moles of gas. Yep, that's right. And if this reacts fully, then I got 2n minus n, 1n. Yeah, 1n of B. 2 to 1. Okay, so I did that right. Okay, the next thing are the mole fractions. And I'm going to go ahead and factor the n's out. Remember, I told you that there is no way that the n's don't come out. And let me just double check my note because I'm doing it off the top of my head. And, okay, this guy's easy, alpha over 3 minus alpha. Now, remember that what you really want are the partial pressures of the gas, right? Because those are right here. And so to do that, since that's mole fraction, you're going to multiply that by the total pressure, but you know I have to divide by the pure partial pressure. So remember that this is the table. Oh, it's squiggly lines today for some reason, I don't know why. PB. All right, and then, all right, now that allows me to define K, and don't forget this. Here, let me just start over here. Writing too much down in a weird way. All right, so now I got to define K. Ow! Yeah, sorry, cat still got my leg. So, okay, so K, before I define K, the AB star, star, remember, what's happened is, this thing, when people were calculating all the delta G's for Hess's law, they calculated it as though the pressures of these gases was 1 bar. So, how they figured out what delta G was, well, I remember they were formation G's. It doesn't really matter as long as everything's done the same way. They would have reacted, whatever makes A and B, the elements that make A and B, they would have reacted them miraculously holding the temperature constant and holding the pressure at 1 bar. And even if they didn't physically do it, which is unlikely, if they didn't physically do it, they took how they were off and subtracted it out and altered the number in the back of the book from what they actually measured such that this works, such that this is 1 bar. Okay, so that means it goes away, but do the reactions in bars. Okay, so if that's the case, and as is, I can also tell you that, I look online to see what other people are doing and to come up with some of the questions. Occasionally I don't just come up with all of them myself because that's not really possible. I see that almost everyone who asks these questions just say, let's hold the total pressure at 1 bar. Now you did do, like in this case, I would maybe start at 1 bar, but I see I'm going to end up at half a bar. And I showed you how to take that into account, but I'm not going to put it on the test. I think that was enough. Okay, so again, it's very common to make these approximations. That makes K is alpha over, so I'm doing B, 2 minus alpha. Sorry, my tubes look like alphas. Sorry about that. 2 minus alpha. 2 minus 2 alpha. So as you see, I've inverted A, and of course I square it. And then this is E to the minus delta reaction G naught per mole over RT. There you go. And now you solve for alpha. It may be done with the quadratic equation, especially if I included pressure as something that was changing, then you had to use Wolfram alpha. So all of you need to bring in smartphones, and no, just kidding. I saw an Imgur, and I'm sure all of you look at Imgur. Somebody had taken their smartphone and put it in the case of the calculator. I thought that was clever. I'm not going to help you on this test. I told you, okay, yeah, this is on the test. Not exactly this, all right? I'm just going to tell you that if you're clever enough, you can set up a reaction. Where's my reaction? You can set up a reaction, yeah, here we go. You can set up a reaction such that this is actually very, very simple. If you set it up exactly the right way, which I know how, which makes solving alpha very, very, very easy. I'm not going to tell you what the reaction is, but trust me, when you are doing this part, because of the way I set it up, you're going to say, oh wait, yeah, that's almost all of it cancels. This is really quite easy. So, okay, but understand this is definitely on the test. So, and what I'm going to do is have you solve for alpha, and I'll give you the G. And I'll ask you about temperature as well, things like that. So, okay. Sorry? You're counter Ryan. Okay. All right, thanks for So again, you've decided the winner, and you forced, in this case, the other one conforms, so it has to flip. And this one was scaled, but that doesn't necessarily mean that that wasn't to get scaled. When I say conform, remember it means that one of them is going to have to be flipped, and that's why you can't just add these suckers up, right? Because I know it's tempting, that's what you were taught. You decide which one's the highest, and then you flip the other one. That's not right, because again, when you were told that, and many of you were told that in analytical, it's because you had the same number of electrons and the scaling didn't matter, but it does matter. So in this case, okay, you've decided the winner, you got the net reaction, you're now at about a C in terms of your grade. Come on, everyone, all right? So now, the way to actually do the math is then I want to see you do this delta G1 plus delta G2. So just show me that you know that this is a Hess's law, and I'm going to do, I'll do the top one. It has a stoichiometry of 1. The Nernst equation has minus number of electrons. I didn't scale it because that was the 2 electron, 0.34. And this is the winner. It's positive, so it stays positive. It didn't get flipped, times farads. I want you to know that farads have to be there. Now the second one is scaled by a factor of 2. It involves, remember the minus sign? It has minus 1 electron. It's got a negative voltage because remember it gets flipped. Remember this is going to get flipped, so that turns minus times a farad, and then this is 0.36 volt farads, and or is it minus? Yeah, no, it's positive, so this is bad. Delta G is positive. Okay, got this far, and I would only take off a point if you didn't remember that the final electrochemical potential is going to be this number divided by the Nernst equation, which is going to be minus. As I have done it here, it's actually a 2 electron Deely, and divided by farads. And so this ends up being minus 0.18 volts. Again, remember the cheap trick, right? Don't forget, this guy is going to be flipped, and then you add them together. And so if that was 0.54, it would have been minus 0.2, but I'm 2 off, so minus 0.18. Totally works. So if you just write down the answer, and you don't show me that you know that this is really a Hess's law, I ain't giving credit, right? Because for all I know, you looked over your neighbor. So I mean, I know that you can do it in your head, and that's why I was kind of flubbing so much that last Friday. It was like my worst day here, in my opinion, because I could just do it in my head. It actually kind of created problems for me, because it is actually that simple. So, okay, I'm almost out of time, but I'm almost out of material, because this is, all right, so then we got the phase diagrams, which are really, really, really easy. And so, and this is recent, so now we're on problem set 10. No, I don't, I think actually I do have this on here. Come on guys, I'm almost done. So remember that planes, lines, or points were defined by 2 plus C minus P, Gibbs phase rule. Why a single component can only have 3 phases, can't have a quadruple point because then you have negative degrees of freedom, Gibbs phase rule, remember that? What else about this? Now, I'm not going to do any of the colligative property-like equations because they're just too stupid and they're freshman chemistry level, but I may ask you, like, what happens when you do that, in which case I want to see you, like, draw this. Oh, excuse me, I'm going the wrong way. You know instantly, remember that even if you're here, your vapor pressure is here, so vapor pressure drops. Boiling point goes up and freezing point goes down. Now you get it all from this one diagram. That I care about. Those stupid equations that had all these approximations that weren't really that good, I don't care about. You did it in freshman, so I'm not going to have you do it again. I do have a reactive system question, and I just don't have time for it, so I'm not going to go over it. So again, look at those reactive systems. Remember that you just write down the phases And I did choose an equation that's very friendly. You know, there's one liquid, one solid, and then gas. Now gas, you're gonna have like two things, and you have to figure out whether they're chemically independent. If they're on the same side of the reaction, they are chemically dependent. So that two becomes one. If they're on opposite sides, it's gonna be two unless the daughter, the product, its atoms come from the reactant. Then that two turns to one again. Look at the example. So sorry I can't write that down, I'm almost out of time. Don't forget this one, let me give you a big hint. Fauzi's clapper on. Okay, now, and that's when dP, dt, and I won't write down the equations. I do have per mole, and from this we could derive the equations for the liquid line, the gas line, and all that jazz, and the solid liquid line. Now, what I've done here, I do have a question that I am going to say, here's the triple point. Is this material a liquid or a gas? And so it's a calculation question. You have the equations in the cheat sheet, and you know that at the partial pressure, when you solve, remember, you do a differential equation, because this is really delta H over T delta V. When you do this, bring this over here, and for like solid gas, liquid gas, you just use the volume of the gas itself, so you use P equals nRT, and so you get an equation for that. And if you find the pressure is greater than atmospheric, that liquid's a gas. That liquid's boiled off and turned into a gas, because remember, atmospheric pressure, you know, it's pushing with its partial pressure, and if it pushes just as hard as an atmosphere, then it's going to escape. So that's the principle there. Now what have I done with this? So I had one of those questions. Here's the other question I have on there. It's tricky. I'm going to have you replace this for a system that's not necessarily a gas or liquid or solid. I could do phospholipids, where instead of volumes you have areas, where instead of pressures you have surface tensions. I could do rubber bands, again tension, length as opposed to volume. So I'm going to give you this, and I'm going to say, now tell me what you think it should have been if I had something else. And it just shows me you know how this works in here. Or avoid it. You have that option. So I have worked in extra optional questions. Last bit, because I'm out of time. When it came to multi-component, remember we had this guy, which did not make the test, and I don't think it's going to. We had the Raoult's law, and then we did that little equation to solve that guy. And what I'm going to do is, on the question that I asked, I give you multiple points. You tell me the composition. I have aligned them to line up with the tick mark very easily and obviously. Of course, the hard part to remember, there's nothing to do here. This is, that's a low pressure. So that's a homogeneous liquid. This is a liquid and a vapor. And, sorry, this is the vapor. This is the vapor, liquid, vapor, liquid, sorry. So the vapor, this is the composition of the vapor. This is the composition of the vapor in the liquid vapor region. This is the composition of the liquid. And this is a homogeneous liquid, again, with, looks like 50-50. Last bit, let me just erase over this, because I know that you have to leave right now. We did two other types of temperature ones, which I remember I said were more interesting. We did complex ones like this, which was a non-ideal solution. I can see that this is two materials that have very strong interactions. I may mix it with a, so this is a liquid, vapor, liquid, gas, vapor, sorry. And then I'll have points. And I'm going to ask, what is at the point? So label the thing, label it like this. Here's the points, tell me what's there. And I also had, this also did in its own way make the test. Don't forget solid. They tend to look like this. There was some variation, but they tend to look like this, where this is the eutectic point. Again, I give you 3 points, perhaps I did, perhaps I didn't. Here you have two metals, A and B. So B A and B and A, so this is Chi A. So here you've got two metals that may be in a solid, it's called a solid solution. And remember I told you if you could look down at like your solder, and you see microcrystals where it's all one metal, and then another crystal facet that is all another metal, so that's called a solid solution. So they're technically pure. Then I've got a liquid solid, so I have solid A floating in a sea of A and B. And then here, again, no lines, it's just a liquid composed of A and B. And remember, this is a eutectic point, which is actually kind of important because that's how we make solder. I may ask you, of course, to label, this is the boiling point of, melting point of A, melting point of B, and eutectic, which is always a bit lower, which is, again, one of the most useful quantities, one of the useful facts about solid solutions is that they tend to have eutectic points where they melt at lower temperatures. It's been a very useful thing I've gone over. I'll try to piece this video together. I'll see you on Friday. Send me emails. I'll answer your emails if I haven't. I'll see you on Friday.